to talk about sugars for all of today and into Friday as well. All right, so we left off talking about stereoisomers. And remember, a stereoisomer is a sugar that has the same number of carbons, but the chiral carbons are different from each other. So ribulose and xylulose would be stereoisomers of each other because carbon 3 is a different chirality. So we also talked about epimers, and that's where we'll start our discussion today. An epimer is a pair of stereoisomers that only differ at one carbon. So I have a bunch of pairs here, and I have a poll for this, but I don't want to put it up yet because I know it blocks some people's view. But I want you to just make a note for A, B, C, D, E, and F for all the pairs if you think these are epimers or not. And I will start with A, sorbose and psychose. So we know, just so we know like what we're doing here. So we're looking for sorbose. Sorbose is down here. Some of the names are cut off, so let me redo that. Fructose, psychose, and tagatose. Right, so we're in A, it's sorbose, psychose, and they are only different at this carbon, this chirality. All others are the same. So yes, these are epimers, true. Yeah, an epimer is where you have sugars that are the same length, and all they differ at is one chiral center. So that's why the two sugars in A are epimers. They only differ at that carbon where your OH has been flipped. It's a different chirality. If it's more than one, then you are a stereoisomer, but you're not an epimer. So all epimers are stereoisomers, but not all stereoisomers are epimers. So I'll give people like a minute or so to do this, and then I'll pop up the poll where you can put in your answers just to see where we're at as a group on understanding this concept. Can I erase my writing? Sure. So a stereoisomer just means that you have different chiralities on your carbons. That's all. I think fructose. You need that one, fructose and sorbose. All right, let's put this poll up. do about another minute or so. All right, let's see what we have in polling. All right. So A, thank you for no jokesters putting false. Thought somebody, at least one person I thought was going to do that. Yeah, so A is true. We went over that. B, sorbose and fructose. So sorbose is right here. Here's fructose. That is false. That is false. So the red carbon is different chirality. You have a OH on the, oh, I'm picking the wrong one. My bad. Before you yell at me, yes, I drew the wrong thing. Still false though. The red carbons are different. So fructose is on the left, sorbose is on the right. The next carbon is also different. Fructose has the OH on the right, sorbose on the left. So that's more than one chiral carbon different. So these are not epimers. So that's false. They are stereoisomers, but they are not epimers. C, rethros and arabinose. That is false. They are not they are not epimers. That is false for that. Let me So I have a question like, how do we answer this? Basically, you're just looking at the two sugars and you're asking yourself, if I'm looking at my chiral carbons, that is carbons that are connected to 4 different things, which side is my OH on? If they only differ on one carbon, they are epimers. So our first one was true. Because if we look at sorbose versus psychose, they differ, and let me get a different color pen. The only place that they differ is on the carbon below the red one, on carbon 3, or 4 rather. The OHs are on different sides of the skeleton. Every other OH is on the same side. So they differ at one carbon. That is a epimer. That's the definition of an epimer. So I'm going to stop sharing results because I need to get this window out of my way. Fructose, D and L fructose. That is false. You would think it's true. Who can remind us which carbon tells us if we're D or L? What carbon do we look at if we want to decide if we're a D sugar or an L sugar? The furthest one from the anomeric carbon. Yes, that's correct. I actually don't know what the Greek lettering system of sugars are. I'm sure there is one, but it's the furthest one, the furthest chiral carbon. So that is the one I'm doing squigglies about. All right, so that is L fructose, or sorry, that's D fructose. That's D fructose. L fructose, and this is not obvious. So there's my 5 carbons for fructose, CH2OH. Okay, so it's L, so the OH is going to be on the left. When I switch this OH, all the others switch as well. The reason why everything else switches, so this is L fructose, is because if it did not go like one direction, then the other two in the same direction, that would not be fructose. So fructose is right, left, left, or left, right, right. And I'm talking about where the OH is. That's what defines fructose. So if I just change the last OH, but don't change any of the other OH positions, I no longer have fructose. So L and D of the same sugar are not epimers. So that's false. Arabinose and ribose, that is true. They only differ at this carbon. And we have ribose and ribulose. That's false because one's a ketone and one's an aldose. So they're not even the same like carbon structure. So that's impossible. All right, any questions about epimers, stereoisomers, how we detect epimers now that we looked at 6 examples? All right, let me clear this and move on. All right, so the linear form, my internet connection is unstable again, huh? All right, thank you, Zoom. So the linear form of sugars is really not the form we're interested in all that much in biochemistry. It exists. The linear form of sugars do exist, but we do care more about the cyclic form. What's epimers again? An epimer is our sugars that only differ at 1 chiral carbon. That's what an epimer is. That's the definition. So we care about cyclic sugars. And the way a sugar cyclizes, those of you who like organic chemistry, here's like the most organic chemistry we're going to get in this semester, is that you have one of your OHs. See, I can do the electrons too. Attacks your carbonyl carbon. And it's shown here as well. And you cyclize, you form a cycle. The former carbonyl carbon, the carbon that got attacked, we call that the anomeric carbon. All right, so that's the anomeric carbon. When we get into a cyclic sugar, we give it a special designation. We either call it alpha or beta. The difference between alpha and beta is you have to look at the anomeric carbon. So I'm just going to call that AC. You see what direction the OH is pointing. You then compare that with the direction the CH2OH is pointing on the other side of the oxygen. If both are pointing in the same direction, so here they're both pointing above the ring, or if they're both pointing below the ring, we call that beta. If they are pointing in different directions, we call that alpha. So you can have an alpha sugar or a beta sugar. For the 4th carbon, how do we know if the H or the OH is pointing up? For this carbon, the H is pointing up, right? Basically up is more or less above the ring. And with the sugars, we're going to look at 2 different types of sugars. Pyranose or furanose, and it's just simply how many atoms are in the ring. So pyranose has 6, so 1, 2, 3, 4, 5, 6. Pyranose has 5, 1, 2, 3, 4, 5. I mean, from the linear form. So that actually does not matter in so much that everything, the thing that matters is that you are consistent, right? So if we look at glucose, carbon 2 and carbon 4 are on the right. So in my drawing, they have to be on both sides of they have to be on the same side of the ring, right? You could draw both of them pointing up if you wanted to. You just have to change everything else to go along with that. So this is a common way to do glucose. You could also do, that H down here, OH, and just switch everything, because these things can move in 3 dimensions. So that's fine. Oh, wait, it's just that people don't draw glucose like this because it looks way uglier. There we go. How do we know which side to put it up? Like I said, it matters that in the linear form, things that were on the right-hand side point in the same direction when they're in a cycle. So here they're both pointing down. That's what really matters. If you want to remember that if you're on the right, you're going to be pointing down, that's fine. I'm just going to warn you, you're going to see drawings out there with OH on the right and they're pointing up. All that matters really is that you have the OHs all pointing in the same direction. But yeah, so you could say right side points down if you'd like. Okay, and finding the anomeric carbon. Okay, we're going to be using the anomeric carbon a ton in these next 2 lectures. So to find the anomeric carbon, the carbon that used to be your carbonyl, you find the carbon that has 2 oxygens attached to it, right? So down here in my pyranose, that carbon's connected to 2 oxygens. In my pyranose, they're connected to 2 oxygens. So that's all that really matters, or that's how you find your anomeric carbon, rather. It's connected to 2 oxygens. So any questions about our terminology here, or how to cyclize a sugar? Okay. The anomeric carbon is the one that gets attacked by your OH. It's your former carbonyl carbon. Yep. That's your anomeric carbon when you form a cycle. Yep. All right. So here is an exercise. Draw the furanose and pyranose forms of ribose. So ribose is this one. Whoops, sorry. Mea culpa. See if you can draw that in a furanose and pyranose. One sec. Would you ask us to cyclize in sugar in words or ask us to show you? So words I could see where I ask you, like, how does that happen? And that's just an OH attacking your carbonyl carbon. I could also show you a linear sugar and say which one is my correct cyclic sugar. I could see something like that too. Or a question like this where I say, which one's furanose ribose? And since we're a little behind, I'm sure nobody's had the time to draw. Let me do a little speed here. One, two, three, 1, 2, 3, 4, 5. Okay, I'm going to draw the 6-membered ring first. Okay, 6-membered ring means the OH on the very bottom attacks. Bam. And so what you get then is, yeah, they're all pointing in the same direction. So O carbon, that would be my anomeric carbon. So 1, 2, 3, 4, 5. So carbon 1, 2, 3, 4, 5. And they're all pointing down, OH, OH, OH. And this will just have 2 hydrogens on it. So that's carbon 1, 2, 3, 4, 5. You don't really see this form of ribose like ever, but theoretically you could draw it like that. Yeah, that should be fine. Okay, what you see though is the 5-member ring of ribose, which I'm going to draw in a different color. So let's do burnt orange, or better known as orange. So in the 5-member version, you have carbon 4 doing the attacking. So we have our oxygen, carbon, OH. There's our anomeric carbon, carbon 1. Then 2, 3, 4, that's what did my attack, so that's in the ring. Then you have a CH2OH hanging out, and then it would be down, down. Those of you who have remember your DNA RNA structures, what I drew should just look kind of familiar to you, right? I just drew the sugar of RNA, ribose. Ribose in the 5-membered ring form. So any questions about how our sugars cyclize now that we see like it in action? Ribose. All right, so the ribose I drew, was that alpha or beta? The 5-membered ring ribose. Alpha ribose, or is that a beta ribose? That's beta. OH is pointing up, CH2OH pointing up. They're pointing in the same direction. If they're both pointing in the same direction, they're beta. If they're pointing in opposite directions, they're alpha. So in red, I'll show you alpha. That's what alpha looks like. That wouldn't be there. Right, so you got to find the anomeric carbon, which is carbon 1, and then the CH2OH and ask which directions they're pointing. So with this red, I just drew alpha. Both pointing in the same direction, beta. It's the OH and the CH2OH. That's all that matters. And what can happen is that when we cyclize our sugars and the sugars by itself, it can switch between alpha and beta. So here's our alpha sugar, here's our beta sugar. This opening and closing event for monomeric sugars happens all the time. Inside your body right now, if you just had lunch, you still have glucose flowing around in your blood. And this glucose is in the monomer form. And most of the time, I forget the exact percentages. It's been a couple of years since I looked it up, but let's just say about 70% of the time, it's in this cyclized form. 30% of the time, it's in a linear form. And what could happen when this linear form reopens, right? The OH that's doing the attacking can attack from either side. It's hard to show in a 2D image, but like it can attack here or it can attack here, which means in a real life monomer, alpha and beta are constantly switching, right? So it's like glucose aren't always alpha, glucose aren't always beta. There's preferences. There's definite preferences. Beta is more preferred for glucose. But yeah, I think that's right. I think beta is more, is it? Yeah, I think beta is more preferred for glucose, but they can switch. So we just need to do a little bit of practice. I have 4 sugars here. Let's see if we can do this question. Yay, I do have a poll for this. All right, my 4 sugars. We're looking at alpha or beta sugars for A, B, C, and D. Oops. All right. It seems like everybody's pretty much in agreement, except for maybe 2 people who had their alpha and beta switched. All right, so I'll just go over this super quick. It seems most of you got it. OH pointing down, CH2OH pointing up. They are pointing in different directions, alpha. OH pointing up, CH2OH pointing up, same direction, beta. OH pointing up, CH2OH pointing up, same direction, beta. OH pointing down, CH2OH pointing up. That one's a little hard to see, to be all honest, but you're really just looking at this guy pointing up. So that is alpha. All right, any questions about that? Not, we'll move on. This alpha and beta stuff will actually be very important here when we talk about polymers of sugar. So it's very good that we understand, just looking at the monomer, how can we tell alpha or beta? Now, inside the body, sugars can be modified, and they get special names based on their modification. And some of these, you should already be aware of the modifications. So why is D beta? Did I say beta? I thought I said alpha. D is alpha because they're both pointing in the same direction. If I said beta, I meant to say alpha. Anyways, so modifications. If you lose an oxygen, you're called deoxy. And we should, whoops, sorry. My bad. I hit the wrong button. Let me pull that back up. Okay, so lose an oxygen, you become deoxy. All right, get a carboxylic acid, that's a gluconic or a aldonic acid, right? And basically you just, instead of glucose, you call it gluconic acid. So you just add that conic, and that's if your C double bond O goes to COOH. If your last carbon goes to COOH instead, that's a uronic acid. And again, we're looking at glucose here. So instead of glucose, it's glucuronic acid. So that uronic acid is telling you what change has been made. If you lose your carbonyl carbon completely and you just become an OH, you're called an alditol, right? So we have ribitol, xylitol, and everybody's favorite, if you know about lipids and the metabolism, glycerol. So I'm not going to ask you like specifics, like I'm not going to show you an image of ribitol and say, is this ribitol or xylitol? What I might show you though is give you an image like that and say, is this an aldonic acid, a uronic acid, an alditol, or an amino acid, amino sugar? So I just want us to know the differences. Xylitol, those of you who love sugarless products, sugarless gum, this is the sugar in sugarless gum. That's what makes it so sweet, xylitol. And then we have amino sugars, where you just replace one of your OHs with an amino group. Glucosamine, those of you who have bad joints or have older pets, you might know what glucosamine is. We'll talk about that probably on Friday. And here we have galactosamine. So these are just some of the modifications. There's a lot more, but these are some of the main modifications of sugars. Any questions about the modifications or what I'm looking for in this slide? Ribitol and xylitol, what's happened is you take this C double bond O and you make it an OH group instead. So you have reduced your aldose and your ketose to a hydroxyl group. And xylitol's in sugarless gum, which I love, by the way. Sugarless gum is so good. Any other questions? Reduce, that has to do with oxidation and reduction. So when we look at like the carbon, +1. So the oxidation number of carbon and carbonyl carbons +1. -2, +1, +1, +1. That would be -1. In a OH, CH2, it's -1. So it's gained electrons. Oil rig reduction is gain of electrons. That's what reduction means. The CHO becomes CH2OH. Yep, exactly. Any other questions? There goes all the dogs. Who would dare ring somebody's doorbell at... Teaching at home is fun, kiddos. All right. We're going to actually skip the next question where you just have to draw like a thio sugar. And a thio sugar is you replace the OH with an SH. But we got more important things to get to. So we're going to skip question 5. What we want to get to, though, are glycosidic bonds. A glycosidic bond is when sugars are connected. So if we want to make a disaccharide, that is, we want to combine two sugars together, the actual bond that connects them together, we call that a glycosidic bond. And there's two types. There's an O-linked and an N-linked. In our DNA, our sugars are connected to our bases via a N-linked glycosidic bond. It just means nitrogen. All right. When sugars connect to each other, they connect via an O-linked glycosidic bond. That is, the the atom that is connecting to the carbon is an oxygen. Really, a glycosidic bond is basically any group that's connected to a sugar. That we call that more or less a glycosidic bond. They're very hard to break. It's like a peptide bond. Once formed, it takes a lot of energy to break these bonds. So they're rather stable. Like I said, when you connect two sugars together, it's a disaccharide. If the glycosidic bond is between both anomeric carbons, it's non-reducing. So non-reducing is both anomeric carbons of a disaccharide are in your glycosidic bond. If that's not the case, we call it reducing. Yes, it's a covalent bond. That is correct. That's why it's so hard to break. All right, any questions about that terminology? DNA, it's non-reducing because both anomeric carbons, well, it's not a disaccharide, but the sugars are non-reducing because their anomeric carbons, which are right there, are in bonds. They actually lost their hydroxyl to connect to the base. They lost their carbonyl carbon to connect to a base. So technically, they would be non-reducing. You wouldn't really use that terminology, though. That terminology is really used if sugars are connecting to each other, but you can use that same idea. Are my anomeric carbons in a bond? If so, non-reducing. It applies to sugars being connected, yes. The difference between O-linked and N-linked is just what element is connected to my sugar, right? So here in our example of DNA, where my sugar is connected to the nitrogens of the bases. So that's N-linked. While here, what's going to happen is this oxygen is going to attack this carbon. So it will be carbon oxygen. That's O-linked. All it is telling you what element is attached. And you can only have two types. There's only N-linked glycosidic bonds or O-linked. You're never going to find like a carbon-linked glycosidic bond. All right. So all we're going to do right now for our next problem is just to figure out, do we have reducing or non-reducing? Here are 4 sugars. Tell me, and you don't have to say it in chat or anything, because apparently I did not make a poll for this for some reason. Tell me, or write down, if you think A, B, C, and D, are we looking at reducing sugars or non-reducing sugars? And I'll do A for us, just in case you're a little lost on my explanation. The first thing you want to do is you want to find the anomeric carbons in each sugar. And it's the carbon connected to 2 oxygens. So this is my anomeric carbon because it's connected to oxygen here, oxygen here. My other sugar, this is my anomeric carbon because it's connected to oxygen, oxygen. Both of my anomeric carbons are in a glycosidic bond. Therefore, this is a non-reducing sugar. Right, see if you can follow that for B, C, and D. Yep. So you don't have to say it in chat. You can just write it down on a piece of paper and then I'll give the answers. Can you have more than 1 anomeric carbon? Not in a monosaccharide, because the way these things cyclize, I'll just draw something super simple here, is that you have an OH attacking your carbonyl carbon. Your carbonyl carbon is anomeric. In disaccharides, each sugar has a anomeric carbon. So in B, anomeric carbon, because it's connected to oxygen. Over here, there's our anomeric carbon, oxygen. So we have a free anomeric carbon. This anomeric carbon is not bound to anything. We call this reducing. And just why they call it reducing or non-reducing, it's because if you add a special reagent, the reducing sugars will reduce that agent, non-reducing sugars won't. So that's how it gets its name. O-link glycosidic bonds include an oxygen. If you're N-linked, you have a nitrogen, like we saw in the DNA. All right, C. My anomeric carbon's right here. And for my other carbon, it's right here. Oxygen, oxygen. So this is non-reducing. D is also non-reducing. The anomeric carbon is not bound to anything. So if you're a monomer, by default, you're non-reducing. All right. Any questions about reducing, non-reducing, how we find that? So non-reducing, non-non. B is reducing because the anomeric carbon right here is not bonded in the glycosidic bond. So if you have a free anomeric carbon, it is reducing. A, C, and D are non-reducing. So you're just asking the question, are my anomeric carbons in a glycosidic bond? If you have one free anomeric carbon, you're reducing. That's all it takes. You can have 99 bound anomeric carbons, but if you have one free, then it is a reducing sugar. Okay, so we're going to move on to our next PowerPoint here. Yay, at the very end of the class, we got the Wednesday. Yeah. So we just looked at reducing versus non-reducing. Now we have to learn how to name this linkage. And it's super easy. What you do is, if it's an anomeric carbon in your glycosidic bond, you have to call it alpha or beta. So here we have our bond going up, CH2OH going up. So we call this bond beta. Then you say what carbon it's part of. So beta 1. And then you see what it's connected to. So carbon 1, 2, 3, 4. So this lactose, the glycosidic bond is beta 1, 4. Sucrose, well, we have our anomeric carbon down here. It's in the alpha position, so alpha 1. Then our anomeric carbon is actually carbon 2 for fructose. It's in the beta position. You can tell it's beta because the bond is going down. CH2OH is going down. They're both pointed in the same direction. So this linkage is alpha 1, beta 2. All right, so this is something that confuses people every year. So let me touch on it. You only use the alpha and beta designation if your anomeric carbon is part of a glycosidic bond. Here in lactose, you can see we have an anomeric carbon that is in the beta form, but you would not call this beta 1, beta 4, because this glucose could reopen to be linear and then reform back to alpha. While galactose cannot reopen up because the anomeric carbon is bound, right? So if anomeric carbon is in glycosidic bond, you have to call it alpha or beta. If it's not in that bond, you will not give it that designation when naming these sugars, these disaccharides. Questions about that idea? And of course, I'll have some practice. All right, let's do some practice then. At least I hope that's the next slide. Yeah, it is. Name these linkages. Are they reducing sugars? So I'll do number 1 just to show you what we're doing, right? First thing first, always find your anomeric carbons. Anomeric carbon and anomeric carbon. Again, is connected to two oxygens. And once you find your anomeric carbons, well, let's just focus on the left. The anomeric carbon in a 6-membered ring is always carbon number 1. In a 5-membered ring, it is always carbon number 2. All right, so we have to start naming. So our anomeric carbon is in our bond. The bond is pointing down. The CH2OH is pointing up. They're different directions, so that's alpha 1. And we see what it's connected to. All right, so I have to start numbering my carbons. So anomeric carbon's number 1 in a 6-membered ring. Then you go away from the oxygen to start numbering. So this one's number 2. Brown's a poor choice, isn't it? Then this is number 3. This is number 4. So this is an alpha 1,4 linkage. All right. See if you can use that strategy to name B, C, D, and E. What does the shape of the bond mean? The shape just tells you the direction that the OH was pointing. That's why it's like, oh, this line is pointing down. So that means that the OH was originally down. Erase. Again, no need to put your answers into text. You can just write them down and I will give them to you in like a couple minutes just to see if you're on the right track. But let's see if we can figure out B, C, D, and E here. Oh, now are these reducing sugars? I forgot about the second part. So free anomeric carbon on A. So this is reducing. Those of you who want to take the MCAT, well, you're going to be looking at a lot of sugars, that's for sure. They love those sugars on the MCAT. So B, let me just find my anomeric carbons. Anomeric, and that's going to be U anomeric. Right, so pointed up. So that's beta 1. So they're pointing in the same direction. If it was pointed down, it would be like straight down, like we have in A. But it's pointed to the side, so the side means up. So this beta 1, then 1, we're going away from the oxygen. So 1, 2, 3, 4. beta 1,4, reducing. Basically the same thing in A, but the anomeric carbon has switched from alpha to beta. C, there's one, and there's it. So it's pointing up, pointed up. So that's beta. Internet just crashed. So let me go through those answers really quick. All right, even though it says I don't have internet access still. Okay. Oh, it's still recording. Fantastic. So C, let me do this really quick here. So C is pointed up, up, anomeric, anomeric. That's 1, 2. That would be beta 1, 2, reducing. Yeah, I'll do B. I didn't realize that that wasn't recorded. Sure. So B, anomeric, and then anomeric, pointed up. So that's beta. If it was pointed down, it would look like that. So beta 1, then 1, 2, 3, 4. That's beta 1, 4, reducing. Yeah. So D, first thing first, find the anomeric, and the anomeric's right there. So carbon 1, pointed down, pointed up. So they're different directions. So that's alpha 1. And then 5-member ring, the carbon on the outside is number 1. So that's 1, 2, 3, 4, 5, 6. This is an alpha 1, 6, and this is reducing. The only thing that's non-reducing is when you have a 1, 1, if they're both 6-membered, or if it's like a 1, 2, or a 2, 2, if you're dealing with 5-member rings. If the alpha carbon is in a glycosidic bond, both of them, that's non-reducing. So any 1, 4 is always going to be reducing because the anomeric carbon is either number 1 or number 2. All right, E, last one. Anomeric. Anomeric, even though it's in a line. So this is pointed. Yeah, I forgot. Sorry. It's been a while since I've done my organic chemistry, folks. Don't yell at me. That oxygen is actually pointing away from us because it's a thin line, while this OH is pointing towards us. So they are opposite directions. So this is alpha 1, 3. 1, 2, 3, 4, 5, 6. Alpha 1, 3 reducing because the anomeric carbon is free. All right. Questions about any of those? And I can guarantee if you look at all my old tests, I always ask questions like this. So I'll give you a 200% promise. If I do not give you this question, I'll just give 100% to everybody on the test. But I'll give you a question where I'm asking you to name disaccharide linkages. You mean an E? Because the anomeric carbon is the carbonyl carbon. It's the same thing. It just hasn't been attacked yet. Only in a cyclic sugar is it connected to 2 oxygens. In the linear form, it's the C double bond O is that carbon. Why do some 1, 2, 1, 3, 1, 4 have an arrow and some have a dash? I don't know if I exactly know what you're getting at, but what you might be getting at is just different projections, different way to show sugars. Like this is that chair and boat way to show it, where we have like dashes. This is, I believe, Hawthorne way to show sugars, where you have dashes and slices. The slices mean it's coming at you. So if this sugar is on the page, anything with a big old dash is coming straight toward your face. Anything with these lines are going into the page. Right. And here, if we're looking at sugars, if it's pointing down, you can think that is above the ring. Pointing to the side, you can think that above the ring. Again, yeah, there's like 3 different ways you can show sugars. For example, it says beta 1,4 dash linked whatever sugar, alpha 1,4 and linked. Oh, are you talking about like alpha 1, beta 2, like that, versus alpha 1, 4? Okay, I get you now. You draw the arrows, you draw a double arrow like that when there's a when it's non-reducing. If it's just an arrow one way, like I can do that versus that. There's like no difference. There's no difference between a dash and an arrow. Yep, the double arrow though does mean a difference. That means it's non-reducing. What was A? A is, let's see, 1, pointing down, that one's up, so that is alpha 1. And then anomeric carbon here, 1, 2, 3, 4, alpha 1, 4, reducing. So everything here is a reducing sugar. All right. So that's all for me because I have another meeting. So I'll post this online. I'll put the homework up. That might not be up till like 4:30 or 5 for those of you who like to get an early start. I apologize for that. Otherwise, I will see people on Friday. As always, let me know if you have questions via email. I'll be happy to answer those anytime. Otherwise, yes, you still have your reading guide due Friday. I'm going to be hustling these next couple of days, but we can make it. On that, I will see everybody Friday. Take care.